So let's see how to solve this problem today. This is longest duplicate substring. Given a string S, consider all the duplicated substrings contiguous. Contiguous means it should be continuous. S that occur 2 or more times. The occurrences may overlap. So it's banana ANA. So this is overlapping. So here you see ANA and ANA are overlapping. So that's okay. Retain any duplicated substring that has the longest possible length. Okay, so we have to find duplicated substrings, but they should have the longest possible length. The answer is, so if it doesn't have a duplicate substring, the answer is a empty string. So it doesn't have a duplicated substring, it has an empty string. So we are given the possible lengths, and we are given this. Notice this, we are said that the string will only have lowercase English letters. Before we look at the hints or the related topic is before we look at that, so let's see an example. So this is a long string, somewhat a long string. So suppose we are trying to find a duplicated string. So if you really look at this carefully, you will find that cat is duplicated twice in this string. So we have to find the longest duplicated string. So if we look at this, if we suppose we didn't look at the hints or the related topics, how would we solve it? So we can just start off with, so we can start off from here and look at all the string lengths from WC. So we can start from the longer length. So we can start from this one, from the entire length of the string, and say there's no point, right? So we can 1 minus the entire length of the string, and then we can search for that, and then we can find search for the next length, and we can search for the next length, and so on. That's a brute force method. So to improve this search, what will you do? So you are going to search this string. So you want to search a duplicated string. So how will you implement the search part? Let us implement the search part. So I'm searching for a 4-letter string. So first I get this will. So first I get this will. So I will search for will, and then I will search for will see, and see if it is equal to will, equal to something that came before it. So I will search for C A L L C, and then see if something came before it, and if it came before it, we know. So how do we search it? So we can use a map. We can use a hash table. So we can add will to a hash table, and then when we come to ILLCA, we can look in the hash table to see if we already saw ILLCA. So will was in the hash table. If it is not there, we can add the ILLCA back to the hash table and search for the next string. So when we see cat when it is a 5-line string, we will head this one, and when we come to this position, we will see in the hash table that it is there. So we'll keep track of a string variable that will have that will keep the max longest string. So we'll proceed like this. Okay, you can use a map. So if we just try to look at that, will improve a lot. We can so if we try to search for will, or for we have will, and we if we search the entire string for will, that will take n squared. So because this is not a sorted string, that's going to take n squared. But so if we search for will, that's going to take n squared, because in this string is not sorted. So if we use a hash table, we can bring that down to n. So searching will be done in n time, or n complexity. But now the problem is we have to search for all the lengths. If you go and search for all the lengths, but there's a subtlety, but it won't be O n, because we are looking through the hash table for each string size. So it's a small string size into n, it will be like that, something like that. Let's forget about that. We'll come to we'll analyze the more optimized version soon. So how can we improve this? So if we are going to search for all the lengths, so if it is from 1 to n, if we are going to search for all the lengths, so n 1 plus 2 plus 3, that's going to be n squared. And then if you doing the search will be ns, it will be, the complexity will be high, going to n cubed and so on. So what I'm suggesting is, for all lengths, search for the string. So search is done in, for each size it will be like for the size times n. For each size, for the length of the string, we are searching for the size. So it will be like, for lookup on the map will take in s is the small string, so it will take s into n. And for all lengths, this going to be, size is going to be 1 plus 2 plus 3 plus 4 plus 5 6 plus, that's going to be n squared. So that's bad, that's going to be n squared for all lengths. So how can we improve that one? So that's where we can use binary search. So now we can look at this. If you look at the related topic, it says binary search. So that's where we can use binary search. So for all lengths, so we'll search for half the length. So we have this much, we'll search for half the length. And then when we find if there is the string that matches half the length, then we know we can mark, if half the length is duplicated, we can mark that as this is getting duplicated. And then we can search for 3/4 of the length. Okay, if it is duplicated, and then you can reduce that distance by 2, like binary search. So you can, so if half is not duplicated, we can reduce the size to 1/4. So we can do this, we can finish it off in log n time, if you get what I mean. So you can use, if instead of searching all the lengths, for all the lengths search, do binary search, do for lengths get lengths from binary search and do the search. Binary search, so that will be log n times, so this will become n log. So this 1 plus, so if you remember amortized analysis, this will be 1 plus 2 plus 4 plus 8, so and so on. So this sum will be equal to on. So that's going to be equal to on. Sorry, this is not right, so it's still, this is going to be n squared. This is going to be n squared. So complexity is going to be n squared. That's not n squared. That's not great. So we want to bring this can we bring this complexity down to probably n log n. So let's see that. So let's see so we have this hint here. If there is an answer, so binary search for the length of the answer. If there is an answer for length 10, then there is an answer for length 987. So we can have if there is an answer for length 10, we can search for 15 if it is increased by binary search and methodology and search for the length. So to check whether if the answer length k exists, we can use the Rabin-Karp algorithm. So this is where normally we are not supposed to be, I don't know, this is not, this is only taught in advanced classes, but it's nice to have a knowledge of this algorithm. It can come very handy. So I have I have found these videos to be very useful to understand this. So we have this, I'll share this videos. So we have introduction to algorithm course from MIT. So this lecture on hatching with chaining and table doubling after Rabin typically covers to some extent, and then we have this recitation video. This rolling hashes amortized analysis, this part covers that Rabin-Karp algorithm. And if you go to, this is a free course. If you look at this, this is free course, algorithms part 2 on Coursera. This is a free, so anyone can enroll this one. So there the professor has used this under the section for substring searches. He has mentioned several of the methods, and one of them is Rabin-Karp. This is very useful. So basically what Rabin-Karp helps doing is, from S into n, it will bring that to S plus n. See, so when you make it this S plus n, this will become 1, 2, 3 n. So this whole thing will become n log n rather than n squared. Okay. So how does Rabin-Karp work? So how Rabin-Karp works is, so in normal searching of the window, so if we have we are going to use a hash map. So we added will to the hash map. So when you this is the answer. So we added cater to the hash map. So when we came for each of this, when we search the hash map for cater, So for if we search the sum C, so if we search the hash map for this characters, we'll see that it takes s times. So searching a hash map still takes the size of the smaller string. But if you put the hash of this one, if you put hash this value, and then if you hash this value and put it in the hash map, okay, so if you hash this, if you hash this scatter and put it as a hash map, and if you hash this pet value and put it in the hash map, there is lot of in hash, if hash is very small, it fits into an integer, so the lookup for this is O1, okay, so it doesn't take so much. So we know in O1 time this doesn't exist in the map, so it will make the lookup of the function fast. But still we are going to be looking at all the sizes now, so we'll see. So we have to hash this one. So hashing, so what Rabin-Karp does is make this hashing fast. So if we are going to hash everything like this, and for all the sizes if we are going to hash, it's going to take the length of the string. But how can we make this hashing faster? If we make the hashing faster, then we can improve the lookup and the search speed. So here if we hash this one, that's going to take O, so that's going to take the size of the small string. It's going to take over s time. So s is the size of the small string and is the size of the large string. But after that we can reuse this one. So if you hash this one, so if you hash this one, all you are doing is adding a and removing w. So Rabin-Karp does is it gives you a faster method of getting these hashes in O1 time. So you don't have to spend 5 character to get the 5 character hash in continuously. You don't have to spend s time. You just spend O1 time. So searching for this string will be done in just the length of the string. It's going to be n, s plus n. So initially we need to first calculate this one, after that it's always O1, so that's s plus n. So here this Coursera courses code is in this repo. So the professor has given the example here, so I'll share this one also with you. If you can look at this implementation, it does this one for us. So here it does the searching, so it does the hashing. It's some fancy math, so please have a look. So I'll be reusing some code like this when implementing. So let's see how we can implement it. So this is going to be a long code, so let me just go ahead and open up a new editor and create this one. So first let's implement this binary search. So how does binary search work? So you have left is the length initial length is 1. So we are going to search the length of the string. So let's see. So int right will be s dot length. I don't know why they use capital S, and then while left less than right. So this is binary search. If you look at a binary search algorithm, you will see this one. So we find the mid of it, that will be equal to left plus. So to prevent integer overflow, we normally use this formula, or rather than using left plus right over to left plus right, or can overflow, so we use left plus right minus left over to find the mid. And then string, so we'll say we have a result. So we know the mid, we'll have a different function called find, that will find for this one int s comma mid. So we give this function the string and say find result if there is a duplicate of this size. Okay, so we'll have one string that's max string, that's initialized with this. So we are searching for all the strings of this length mid and seeing whether there are strings of this size duplicating. If it is duplicating, this will return a result. If not, it will return an empty string. So if empty string equals res, that means we don't have a string of this size, so we will reduce the size of the search. Okay, right equals mid. If there is a result, then we will increase the size of the string, that will be equal to left. So our max string will be equal to result. So always we are going for the longer length if possible. And then left will be equal to mid plus 1. So that's for this one, and then we can return the result max string. If something is found, we know that we can return that one, otherwise we'll return an empty string. So now what we have to do is implement. This is so simple. So we search for a length, we search for that find method, and we return the result. So simple binary search. Now the difficult part is implementing the find. So let's see how we can implement a find. So I'll create a new function, private string, so it returns a string, and then find, so a string str, and this will be the size of the string. Let's implement this one. So in Karp Rabin, I didn't go in detail for the Karp Rabin algorithm, but in Karp Rabin we need a base. since our characters are only 26 characters, so it will have a base of 26. So we'll create this string with a base of 26, and then we need the power. We had to find the power of so if I can show you the algorithm, if you look at this one. So here we need to find this algorithm. If you look at this one, so we need this is the part this is the one that removes the leading digit. So we need this text hash, and then this value is the size of the string. So let's see, so I'll write it here. So that's rm is equal to base to the power size of the smallest string minus 1. Okay, to find that one we can use something like this. So I can use so this can why we are using for loop to find this would be, so there will be a prime. We need a prime. So this algorithm calculates the hash of maybe a very large string. If you calculate the hash of a very large string to the base 26, it will grow very long. So we normally mod it to a prime, mod it with a prime. So this prime we can define it here, private final private static final prime, and then we can have it initialized in the we can have it initialized here now. So we can get a very large prime using this method. So if you look at this one, big integer, you can see if you search for probable prime, you can see there's a function here, probable prime that will give us a prime that is probably possible to occur. It will give a prime of this bit length. So I can use that one here. So big integer probab. So let me copy paste this one. And then the best possible pipe length of the prime would be 31 bits, but for practical reasons, which I will show you in a bit, I will use a prime of length say 15, and we need to pass a random value. You can create a new random, or I will just use this thread local random current, and then I need to get the int value, and then we'll use that one to calculate the rm is the base to the power m minus 1. So you can call it bm or whatever. I called rm because the Coursera course had used that one. So let's calculate this power I less than or equal to size I plus plus. So if you look at this one, so we need to first calculate this one. So it's going to be size minus 1. We don't need a very large value. So I will calculate this power Rm into Rm to the power base, and the reason why we are doing it, we are using this and not the power function that was given by met. We can use met dot pow, but we are using this. You are using a for loop to calculate this because we have to mod it by prime. Otherwise, this can grow very large and beyond the size of integer. That's bad. So we are getting the 26th power. That means 26 to the power to the size of this one. That's like can grow really large. This is we can add a comment here, base to the power size minus 1. That's this, and then we'll do this. We'll initialize a map. So we'll have a map like to do the searching. So why we are having a list here is because of possibility of collisions. So if two hash, so we are comparing hashes, not the actual strings. So multiple hash values can go to multiple strings can map to the same hash value. So we are using this list for that for the possibility of having multiple hashes go to a single location. So we'll have this int hash. This is the running hash. That's going to be initially 0. That's running hash. So initially we need to like first calculate. So if the size is given to be 4, we have to first calculate the hash of this one. After that we can you reuse that value to calculate the hash of this one. So initially we need to calculate that first hash. So that's done like this for int I equals 0, I less than size I plus plus. So it's going to be running so hash is going to be equal to you have to this formula is so this is division method of calculating the hash. So hash into the base plus, it's like how you will be doing how you will be calculating the hash for any base. So base is 10 means you will be using the multiply it by the base and then add it by the value of the char. So I will create a new function called get value. Provide so int get char num char c. So we need to convert this char to a base 26 value. So I have written this one here, and then get char, oops, that was, so get char num, and then str.char at I, and then let's calculate the mod of it. So because this can grow very large, this sum, if we go on summing this one, this can grow very large, so we'll calculate the mod of it using the prime. So I will add the mod by a prime here to make this grow smaller. So if you look at this, the reason I used such a small bit number is because you know, this value can grow large now, this multiplication. If prime is a 31-bit number, so base can be 31 bit, hash can be 21 bit, then this multiplication can grow beyond the size of the integer, and this can cause an overflow. So that's why I am using as 15-bit prime for practical reasons. Theoretically we can use 31 bits. If that is the case, we have to use a long for hash and base still like that. There is other concerns also, so I'll just use prime as 15-bit and then calculate this like this. So this will append the character, this will remove the character, and this is append the character. Now we need to search for that string in the, now we have a new hash. Earlier we added this hash, first hash. So if you look at this one, so I added this one. So if you look at this now, if you look at the example here, we added will, so we need else. So we now calculated the hash for else, and then we need to see if ILLC occurred earlier. For that run, we can check our map for this one. So I will continue this code. So if map contains hash, so we'll have to search for the hash in the, sorry, it was some undo, so that something went wrong. So we will search for the so each map has a list, so for each position in the list we'll get search for our string. So I will use a method called check to check if that this string and the other string are matching. So current string position is I plus size, so current string position is I minus size plus 1. So if you look at this one, it starts from size. So if you from the first character to size, I minus size plus 1, and the other is the position of the other string, and then the size, return. So if this check is successful, if they are equal, this check is to check if they are equal, return the substring of this value. Substring, I want the substring from other to size plus other. This is the string that is duplicated, the scroll. Okay, so if map doesn't contain this hash key, we need to add it. Obviously in this case we are going to edit put hash comma new array list, and then we need to whether this if this check doesn't succeed, it will come here. If after this also it will come here, so we'll add to our list. The position of the string is I minus size plus 1, as we saw before. And then if the string is not found, we will return an empty string. Okay, now we need to write this utility function check. So I will write this one quickly. Private it returns a boolean check. So it will check like from it will take this string and then int L, int M, int size, and it will check the string beginning at L and M. So for int I equals 0, I less than size I plus plus. So we have a mistake here. I just saw it, and then I will return this one here. If str.target what is it, I plus L not equals to str.target I plus M, return false. Otherwise the message is written true. That's it for this algorithm. Let's run it and see. So we have a mistake. I noticed a mistake. Private static final int. So let's copy this code and then let's run this in our console, LeetCode console, and see how it goes. So there can be compilation errors. Please excuse if any. So I will run this here. So there is this contains. So there should be an error. So we can't memorize everything. Map dot. Okay. It's very clever. Okay, we get it. So I just copied our example to the test cases and got this result. So I can have banana also and see if it is just ANA. I'll check this one also to see if it returns the correct value. Oops. Okay. That's good. Let's submit this one. So if you look at this one, so it doesn't takes a long time, but still, like, you know, this is this will take n log n time. So this procedure, as you can see, is taking this for loop is taking s the size plus n is the length of the string. So is approximately n. S plus n means n. This is taking n, and this will run for log n time in according to binary search. So it will take n log n time, which is quite good for research algorithm. We can't do better than n log n if we are searching for a string. So this is good. Thank you for watching. Please subscribe for more videos.